Buongiorno, welcome everybody to our February edition of Lagoon, and it's a very great pleasure to have Tristan Bozec from Angers here, who will talk about topological field series via derived algebraic geometry.
Thanks a lot. Hi everyone, and thanks for the invitation. Okay, so I'm going to talk about topological field theories through the lens of derived algebraic geometry. So I won't assume any deep knowledge on either of these two notions. So here, derived algebraic geometry is going to see as a tool to deal with topological field theories. I try not to go neither into too much technicality about either of these fields, so I'm still gonna try to tell you some things. So basically, at the beginning, maybe an overview of how derived algebraic geometry can help with this guy through more or less well-known examples and applications. From time to time, I'll try to speak about my work more precisely. All right, so the beginning of the story, I mean, from my point of view, this is from a personal perspective, I guess, is the so-called AKSZ construction, so from Alexandrov, Kontsevich, Schwarz, Zaboronsky, of course, induced by many physical perspectives. So a field theory depends on some space of fields considered over some manifold X, which will usually come with some Poisson or even better symplectic structure that can be of interest towards some quantization issues, for instance. I won't talk about quantization today much, so that's probably the only time I say the word. And a large class of examples come from what physicists call sigma models, where the space of fields looks like some kind of mapping space from our given manifold X to some target T. Okay, so that already raises some questions from, I guess, from a mathematician perspective. Because, well, I mean, if you're into algebraic geometry, for instance, you're probably not necessarily very comfortable with what a mapping space is. So we'll see that later. That's a big part of the problem. So to state what, in a very simple way, the AKSZ theorem, it says that whenever our initial manifold is oriented in a suitable way, and the target is symplectic, actually the mapping space itself inherits some symplectic structure itself. So the main the construction behind this is called the transgression. And the idea will be the same when dealing with derived geometry. So how do we, the aim is to transgress the symplectic structure from T to the mapping space. So we call omega the given symplectic form on T. We have, of course, a natural evaluation map. And we can integrate the pullback of omega against given fundamental class on X, which amounts to the orientation of X. Okay, and that's how you define something, or well, at least you get a form on the mapping space, and of course the game is to prove that it's non-degenerate to get a symplectic structure. Okay, so to recover the famous theories, so for instance, Chern-Simons theory that we will meet again later when essentially the target is looks like BG, classifying space of a, say, reductive group, or some versions of A and the dual model B in mirror symmetry. These ones I won't talk about much in the sequel. So this is from back in 1997. Uses some kind of pre-derived geometry in a way, but it's a very ad hoc construction, depends on the model. It's not invariant through homotopy. So about this a priori infinite dimensional mapping space, it's very formal, and actually you only consider maps that are infinitesimally close to the constant map. So many issues, I mean, at least from the point of view from someone doing mathematics. Okay, so that's actually all these issues I just mentioned are really well dealt with using derived algebraic geometry, and more precisely the symplectic variant, which is called often shifted symplectic structures. Okay, you don't need much assumptions. It's very much independent from the model you pick. And we actually have nice mapping spaces, actually mapping stacks, and that we'll see later are very well suited for manipulating TFTs. So we'll see field theories as functors. So we're actually on this slide dealing with objects of some categories I'll define later. The crucial theorem established by Pantefto and Vaki and Vizzosi is really the analog of the theorem I gave on the previous slide in a derived setting. So here X is still something compact and oriented in a good way. So it's going to be a derived Artin stack. And when T is shifted symplectic with some shift given by some n here, then the mapping stack is itself shifted symplectic for some precise shift given by n minus d, okay, d being the dimension of x. So just in a line below the theorem here. So what does it mean to be shifted symplectic? It means that we're gonna need not only tangent or cotangent spaces to our object, but tangent and cotangent complexes. Okay, since they're complexes, we'll be able to shift them, and then being shifted symplectic is only requiring that our closed-to form induces a quasi-isomorphism, not being the tangent and the cotangent, but with an eventual shift gives this shifted structure. Okay, so right away with some very basic but nice example. So it has a lot to do with Lie theory, Lie groups. For instance, the killing form on a reductive Lie group induces a two symplectic structure on BG. We're going to be interested in topological field theory. So what can be done with something a priori topological when my theorem applies to derived stacks? Well, I can consider the Betti stack associated to my topological space M. So it's a constant stack associated with singular chains on M. So that the mapping stack from this Betti stack to BG is just classifying the G local systems on my topological space. The theorem says that from the line above, it gives me a 2 minus n symplectic structure on the local systems, which, of course, well, makes a theory sound, recovers the usual zero symplectic structures, meaning the standard symplectic structure on local G-local systems on a surface. All right, so when I consider the circle, okay, so the Betti stack of the circle is just BZ. So the mapping stack is a quotient stack of G by itself with adjoint action. In this case, we get something one symplectic. Okay, of course, the structure can be detailed, amounts to considering the more Cartan forms. And well, we can shift cotangent stacks associated to derived stacks. It turns out that the one shifted cotangent stack to BG is the one quotient associated to the dual of the Lie algebra, which is also one symplectic, because one shifted cotangent stacks are one shifted symplectic. Okay, another class of example. Well, another example is when, well, you know the importance of the Calaque property in this theory, maybe. For instance, when X is K3, so the mapping stack from X to BG means considering the classifying moduli stack of G bundles of on X. So in this case, we recover something symplectic in the usual sense, which is something already known since Mukai. Okay, we'll see more about Calaque stuff later. All right, and so as I said, I aim at considering categories. Here I have some objects, and of course I want to understand what morphism should be. And in symplectic geometry, of course, the relative nice notion is given by Lagrangian structures. I'll start with examples before giving a very blurry definition right below these examples. What's nice in the derived approach of symplectic geometry is that actually we recover moment maps once we consider quotient stacks by the group G. And being a moment map for something Hamiltonian means that we have a one Lagrangian morphism. Same goes for Lie group valued moment map, okay, associated to quasi-Hamiltonian geometry. And again, considering topological spaces, the nice thing is that when M has a boundary, the restriction of local system to the boundary actually produces something Lagrangian. Okay, we want, of course, the target of a Lagrangian morphism to be symplectic. So that's the case here, thanks to the previous slide, and we have a shifted Lagrangian structure. Again, following relative analogs of the previous examples on the previous slides, if I consider some Fano variety and and a divisor which is K3 and anti-canonical in there, the restriction of G vector bundles is something here Lagrangian in the usual sense. So we retrieve this from the derived geometry. So precisely, what does it mean to be Lagrangian with a shift, with target being n symplectic? Okay, so the shift for the Lagrangian structure is always dictated by the shift of the symplectic structure on the target. Well, it means that if I have this triangle or fiber sequence here, it is actually fiber. Okay. All right. So a few very nice features of Lagrangian structures in derived geometry is that, well, as Einstein said in other circumstances, everything is Lagrangian, meaning here that actually being shifted symplectic means that you are actually Lagrangian to the point endowed with a trivial n symplectic structure. And again, with the aim of composing morphism in a category, here you see that if you're just dealing with Lagrangian morphisms, it's complicated to understand how you can compose this. So instead of looking maps, we're going to look pairs of maps with the same source and call it a Lagrangian correspondence or span. Just means that we have a Lagrangian morphism to the product of the two targets here, where the bar here means that you consider the opposite symplectic structure X2. So why doing so? It seems a bit artificial like this. Well, because we're going to be able to compose correspondences. Okay. Well, I guess this is something extremely usual already in, for instance, in geometric representation theory. What does it mean here in this context is that if I have two correspondences with one common target here, I can just take the pullback of this pair of maps here and get a new Lagrangian correspondence. So that's where derived algebraic geometry works very well, is that we indeed get, by using pullback, the shifted Lagrangian structures are preserved by homotopy pullback. So that's really nice. So before applying these to TFTs, let me give you a pair of examples which are actually obtained in the case where x1 and x3 above are just points. That gives you a very famous example, which is the critical locus. So here, this is derived critical locus. Okay, when you take the truncation, you get the usual one. Okay, so you consider a function. The graph of the differential gives you an honest Lagrangian morphism from x to the cotangent. And then you take the pullback with the zero section. The properties I gave above give you a -1 symplectic structure on the critical locus. Okay, so it doesn't make sense if you don't know shifted symplectic structures. So here you get this. It's actually extremely important in the modern approach of Donaldson-Thomas theory. So that's extremely used in the representation theory, the recent development about cohomological algebra, whole algebras, etc., which is not really the topic today, but that should be said. Another example, if on the topological side, if I consider a surface with a boundary given by a bunch of circles, for each of these boundary piece, I consider a conjugacy class. And I can consider the moduli of local systems with prescribable holonomy at each of these boundary part. Okay, so that amounts in doing some pullback. Okay, and I get something the pullback of one Lagrangian morphism from the examples above. Therefore, I get something which is again Lagrangian to the point, so which is actually zero symplectic, meaning symplectic in the usual ways, something already known. But you retrieve this in a very nice fashion, just performing pullback here. All right. So let's take a look at the first TFT. So from the beginning, I'm on in the examples I gave, mostly on the Betti side of the non-abelian Hodge correspondence. So I'd stick to this on this slide. Okay, so a TFT is a functor from some category of cobordism. So here I consider cob D the category of compact d-dimensional oriented topological spaces. And considering as prescribed two pieces of the boundary, one labeled by minus, the other by plus, so that I have actually a cospan. Okay, it's a bit artificial, but that's gonna be what allows me to compose stuff in the target category. Okay, so when I do this, apply the Betti stack and look at the mapping stack to BG, where G is given, I actually get a symmetric monoidal functor between one categories, so the cobordism category and 2 minus d shifted Lagrangian correspondences that can be composed as explained in the previous slide. So here I'm sticking with one categories as written at the end of the slide. It actually fully extends. So the initial story was done by Calaque in 2015 and was extended recently by also Calaque with Hauxeng and Scheinbauer. So fully extends meaning every dimension. Okay, you can consider cobordisms between cobordisms, making corners appear, and again, is compatibility notions, of course, so that everything is infinity categorical. I won't get into these details today. Let me just illustrate what's happening here in genus 0. There's a famous example of the pair of pants, which might be seen as a cospan, a cobordism between one circle, okay, so the top of the pair of pants, which is on the left here, and a pair of circles on the right-hand side. Applying my construction here, I take G-local systems on the pair of pants. So these are just this is just mapping stacked between the B of the F2, right? Pair of pants up to Motop is just a pair of circles which are tangent to BG. So that's just the quotient stacks of G2 seen as a correspondence here between G and G mod G square. Generalizing this a little bit, if I consider the two sphere from which I remove K disks, I can see that as a cospan between one disk and K minus one of the ones. Okay, I can recognize some kind of character stack here, but in genus 0. So I have K guys in G that where with product equal 1. Okay. And then take projections to the K minus 1 first and then to the last one here. All right, so that's for the Betti side. Okay. Then I want to talk to you about a bit of noncommutative geometry. Okay, so following the Koncevich-Rosenberg principles, in each time we have some geometric notion, we can wonder if it's actually induced from purely algebraic notion, applying some representation stack or perf stack to these notions, recovering the standard geometric ones. So this is a now story that is getting longer and longer. I guess as long as we are considering Poisson geometry, the first ideas started either on one way from Kontsevich introducing pre-Calabi-Yau structures with Hugo and other collaborators, more recently with Alex Takeda, for instance. And another approach is the one by Vandenberg, who considered double Poisson structures, which is not using any DG structures. And of course, if we're interested in symplectic noncommutative geometry, can go back to the works of Tingoff, Crowley-Bovy, and Ginsburg, which was not neither in the DG context, but still the fundamental paper of Ginsburg about Calabi-Yau algebra is of course very important. So here I'm going to take the point of view of Brav and Dicker-Hoff. That works in the context of DG categories, and which gives non-commutative analogs of shifted symplectic structures. So how does it work? We say that a DG category or DG algebra is D Calabi-Yau if the shifted dual of A is equivalent to A. Okay, so we're dealing with DG stuff, so it means something to shift an object. The dual here is as a bimodule over itself. And of course, I'm being a bit sloppy here. What replaces two forms are going to be Hochschild classes. Okay, so it's not a property; it's really a structure to be Calabi-Yau. It means that there exists a Hochschild class that induces a map from the shifted dual to A, and we have something Calabi-Yau if there exists a class such that this map is an actual equivalence. Okay, so we really see an analogy with tangent and cotangent complex here. You can think of it as have with the Serre functor in mind, or even the Poincaré duality. And why is there's this terminology of Calabi-Yau is because thanks to ideas of Ginsburg, well, the derived category associated to some d-dimensional smooth Calabi-Yau variety is actually Calabi-Yau in this sense.
Tristan, just a question from the chat. I don't know if you can see the chat.
No, because I've removed everything, but yes,
so
tell me.
There's a question by Shuang Mao who asked, what is the shift of a DG category? As far as I understand, the dual of A is still a DG category.
Yes. Okay, you can think of DG algebras, right? It works the same. There's a grading on the category, and you can shift it. There's no trick in there. I'm not talking about dualizability here, but yeah, think of DG algebras as DG categories with one object, but yeah, it works the same. Actually, in the examples below, we're just going to have zero concentrated DG algebras. So, all right, so there's also a relative analog to this story. Morphism will be called D Calabi-Yau.
Sorry, there was another follow-up question.
Yep.
Does that also preserve Morita equivalences?
What does?
Does it preserve Morita equivalences? Shifting.
Yes. Oh. Yeah.
Okay.
Yeah. So I'm not talking about the models stake here. So I understand it's pretty sloppy. So let's say that our DG categories are smooth and even of finite type. Okay. If that helps. I wasn't precise about that here. Other questions?
Oh, it seems in the moment that there's no other question.
So I'm not giving the precise definition of being relative Calabi-Yau. Exactly as for Lagrangian correspondence, it amounts in requiring that some shorted sequence is actually a fibered sequence. I'll stick to the example motivated by geometry. A bit like earlier, I can wonder. Sorry. Yes, I consider Y. There's some word missing here as a smooth Calabi-Yau divisor, which is anti-canonical in some ambient smooth variety X. Then the push forward on derived categories gives actually something which is Calabi-Yau. Okay, but what matters most is what happens when we are dealing with something just topological spaces. Brav and Dickerhoff actually define DG algebra of chains on the baseless space of M. So notation L comes from the fact that modules, DG modules of these are local systems, but this time of cochain complexes of M. Turns out that if M is oriented, so this DG algebra L of M is D Calabi-Yau. Okay, so that's really a DG variant of Poincaré duality. That's really it. They call it Poincaré pairs actually, M with no rotation. And we get again, very nice, not only Calabi-Yau morphism, but a Calabi-Yau cospan when two pieces of the boundary are prescribed. Okay, nice. So the main theorem of the second paper of Brav and Dickerhoff is that the functor of the moduli of perfect objects, so the same defined by Antef, Toenvaki, and Vizuzzi, so where there were some of these ideas in there, actually maps Calabi-Yau cospans to Lagrangian spans, meaning correspondences. So that's main results that actually authorize us to see these Calabi-Yau structures as very good non-commutative analogs of symplectic / Lagrangian structures. Okay, so small example with our pair of pens here. I can my DG algebra of chains on the pair of pens is given by two invertible non-commuting variables, x and y. And then if I restrict my perf functor to zero amplitude complexes and n-dimensional complexes, I get something we've seen before with G replaced by GLL. What we proved recently with Damien and Sarah is that on the left-hand side here we have an honest TFT, and that actually it factorizes Betti TFT introduced by Damien with this time target just perf K. Okay. Well, we prove a little more than that. That's the point, is that we have some kind of non-commutative version of what was said earlier. Any other questions? So that's, I'm gonna shift direction now. So if there's a question now, take it. All right, so I want to talk now about some the later Moore Tachikawa conjecture. So for two reasons. First, as an example of how shifted structures help with tackling pretty very concrete physics problems. It will kind of also motivate the rest of the talk. So why does it fit well in what I'm discussing here? It's because so the Moore Tachikawa conjecture is how do you say that was about defining some TFT from two cobordisms to some subcategory that I want to see as a subcategory of my one category of one-shifted Lagrangian correspondences. So objects, I want to see them as my one shifted symplectic quotient of G dual at the Lie algebra by G. So of course, in the text of Moore and Tachikawa, the objects are just large capital G, the affine algebraic group itself. But I want to have this point of view. The morphism between two groups is going to be in the initial language just a moment map. From what I said earlier, I want to see that as a Lagrangian correspondence where I am prescribed a zero symplectic variety with an Hamiltonian action. So again, it gets tricky when you want to compose this. Okay, turns out that the original definition was to consider some kind of Hamiltonian reduction here, followed by another quotient stack here. It turns out that it matched the composition I gave in my shifted Lagrangian category. Okay, so that's for the description, and then I can state as a theorem what Cooks and Merrill put on the archive in 2024. That gives me the occasion of actually giving you what is the conjecture. It says that given group G and principal SL2 triple in the Lie algebra associated to G, I can produce a TFT to this Moore Tachikawa category that maps a circle to so here I identify G with G dual, and that maps a cap on the Slodovy slice associated to the prescribed triple. Okay, this is indeed zero symplectic, and this is actually Lagrangian, one Lagrangian. Okay, so the proof uses groupoids, Frobenius algebras, not much the mapping space method. Okay, so what I want to keep from this is that it fits in the framework of a shifted structure, and also that we kind of have instead of on the Betti side having quotient of the group G by itself, here we have quotient of the Lie algebra by the group. So what am I going to do with this is leaving the Betti side to another side. So I won't talk about the Durham shape today. It's totally worth looking at it. We did, so from now on, this is work I'm doing in progress with, again, Damien and Julien Grivaux and Hugo Pourcelot. So we didn't really, we tried to work on the Durham side, so meaning that we work with the moduli of flat connections. wasn't working so well, so we switched to the Dolbeault side. But of course, the idea is that we will first not work with topological spaces, but we have to go into algebraic geometries. We have to work over nodal curves, okay? And what's going to replace the boundary of our topological surface are going to be marked points, okay? Okay, well, I have emphasized that the nodes are not marked in this story. So I'm not gonna do logarithmic geometry per se. I'm just gonna use this pretty classical logarithmic tangent bundle that can be completed along the zero section. Okay, just completion using the addition. Comes with one map for each marked point. Okay, given by these coordinates above each of the mark points. And taking the classifying space, I have what Simpson defined as a logarithmic Dolbeault stack. What's really nice is that it comes with such map, okay, which is actually going to be one-oriented. You might think of it as an analog in the analytic geometry, taking functions taking residues and on functions, and actually the non-degeneracy of the orientation, the homotopy can be seen as the Stokes theorem. It's a bit as when you're dealing with Durham complexes and its shifted symplectic structure. Okay, so taking the mapping space to BG, we get something people in representation theory are very familiar with, which is some Higgs modular space. So of G bundles, all right, with eventual order 1 poles at marked points. Okay, so we have a principal G bundle, and the Higgs field has values in one form answered by the adjoint bundle here. Thanks to the results earlier mentioned of Calaque, the orientation above yields an actual shifted Lagrangian morphism from my Higgs moduli to the mapping space from BGA. And that's where I can, this very final part that explain why I talked about more Tachikawa earlier, is that what's different from the Betti side is that I get the actual Lie algebra here. Okay. So it's a bit complicated to understand without restricting ourselves to some with some precise, some more precise setting. So I'm considering nodal curves, but I'm going to restrict to some to the curves with rational components. Okay, so otherwise, if you consider the normalization, you only have some P1s. And restrict myself to Higgs bundles living above the component of the trivial bundle. That's restricting enough so that we have this pointwise proposition that tells me that the Higgs bundle that I get doing these two things is actually very well described by some quotient with these parameters here. Okay, so it's basically combinatorial on the graph of intersection of irreducible components. You have this. You have to count residues and then take care of some decent data to our original curve. So again, taking a look at genus 0, this time I have these n residues that sum up to 0, and my Lagrangian map to some power of g over g. So the title said some operatic flavor. So where does it come from? When I have two genus 0 marked curve and prescribed marked point on each of these two curves, I can just compose these at the specified marked points, which is blue here, and I get a new nodal curve. Okay. Said otherwise, I consider X with two irreducible components and intercepting as a single. Turns out that my Higgs moduli behaves pretty well with respect to this structure. We say that Higgs, so with this trivial bundle, is an algebra over what is called the modular operad mg bar. I won't go into operatic details here. It's not a big deal if you don't know about this. I'm going to try to illustrate the proof and show you that it's really about geometry and not really about operads, even though they help a lot. So from the proposition here, we can wonder if we don't have something that's actually a local system. What we believe is the first very important step in this direction is something that we formulate in terms of operads, saying that the rational piece we've defined is actually the modular envelope of zero genus curves. Again, you don't need to know what modular envelope means here. I'm going to illustrate this through a proof/example in the following slides. I should mention that we are very much inspired by John Siracusa. It should be seen as an analog of the handle body modular operad, the envelope of the frame, little 2D operad for those who know this guy. Okay, so what do we do? I've already mentioned that it has a lot to do with graphs. I can consider those of genus G. What will play the role of my marked points are just going to be half edges coming out of my graph. Okay, they've depicted this in orange here. And the morphism are going to be contraction along non-loop edges. Okay, basically means that you can contract any tree in your graph. Okay, and you keep whatever's left. Then contracted edge disappear, and I give you an example here. Now it's convenient to see M0 as a functor from this graph to groupoids. Basically means that at each vertex in my graph, I put genus 0 marked curve. Okay, so I want to emphasize that I can have multiple irreducible components at one vertex. Okay, I've decided to draw these as topological surfaces here. Okay, so the graph does not see all the nodes. Okay, I can have inside nodes at vertices of my graph. What does the contraction do? Well, it peaks to so okay, on each vertex I have now two types of nodes, those induced by the half edges and those induced by the blue half edges that corresponds to actual edges in my graph. And I can contracting means that I put two of these blue nodes together, and then it just disappears. Okay, it becomes in the inside. Okay, so that at this vertex here, I have now genus 0 curve with 3 irreducible. Okay, now something a bit combinatorial is that I say that a set of nodes on a given curve of any genus is admissible if blowing up along these nodes gives a union of genus 0 curves. Again, I can see that in a fancy way as a functor to groupoids. Okay. At a curve, I just associate the poset of admissible subsets. Okay. Again, an illustration through an example. Consider a curve with 3 irreducible components with one marked point on each component. Okay, so in this case, each time I blow up one of the nodes, I get something 0 of genus 0. So the only non-admissible subset is the empty one. Okay, so really when I look at this picture, I'm looking at a point in the Grothendieck construction of M0. So this was the previous picture. And then what I can do is going to the Grothendieck construction of my functor n here, which just means that I consider my curve. Okay, so this is just a topological way of looking at this complex curve. We just mean that I have this curve with 3 reducible components, here of genus 1, and I pick some nodes. Okay, so here 2 out of 3, here 1 out of 3, because I have forgotten this one. Okay, so here on the floor level, nothing. Well, on this example, nothing doesn't. It's not much happening. We just consider this node as a subset of these pair of nodes. Okay, so that's a relation in my poset. And I want this thing to be. I'm asking you to believe that my theorem above here means that we want this to be an equivalence. So reverse equivalence here is just blowing up along the prescribed nodes of my in my admissible set. So I'm putting a lot of stuff under the rug here. I have to take some classifying space of these. Also, I want to emphasize that we're dealing with pre-sheaf that actually need sheafification here. So just to finish up, I want to illustrate this with an honest family of nodal curves here that I see over A1. We actually only have a pre-sheaf because you see that sometimes nodes can pop up here, and we would have global sections for here. Here we want to get rid of this guy, which is not a normal curve, but on this side we see that we need to apply the plus construction once, but in the end we indeed have the theorem we want, which is this guy. And I'm going to stop here. Thank you.
Thank you very much, Tristan, for the very interesting talk. Are there any, we should clap maybe. Are there any questions or comments? If you have a question in the audience, just unmute yourself and ask. I had one question, maybe some more conceptual question. At one of the first slides, I think maybe the second slide, I don't know if you can go back there. Or this one. So last example is very interesting. So you take a K3 surface and then you look at this mapping stack. And if you want to consider maybe higher dimensional things of analogs of K3, like hyperkähler manifolds or stuff, is there anything known? Can you analyze these mapping stacks or its geometry? I mean, it's probably more complicated, but
I guess. Well, all right. So you want something which is oriented.
Yeah, maybe.
Yeah, I just wanted to recover some classical example, but there's a lot of liberty in using this theorem. No, a lot of things can be done. I mean, yes. So no. So the TFT here is very as natural factorization. So first there's a you know there are several steps here. So actually proving that you can start with any it extends in all dimensions. So, no, it really depends what your purpose is, but you can.
G is any kind of, say, reductive algebraic group or complex Lie group or something, or what you can put there on the right.
Okay, you want BG to be too symplectic, so you need the scaling form.
Okay.
So that's a constraint here.
Okay.
But you can do I guess that's what John Simons describes. Of course, target can be any symplectic stuff.
Okay, thank you. Any more questions? Yeah, there's one. Do you want to unmute yourself, or shall I just read it? So, I mean, maybe you can see it in the chat now, or maybe not.
I can't retrieve the thing I had removed earlier.
There's a question by Kai Wang. In fact, two questions. So the first one is, I will read it. Is there any relationship between MG-RAT and a cohomological quantum field theory, algebras over the modular operands MG-N, for example? And the second question, is there any explicit description for the homology of MG-N-RAT, like the homology of M0 is hypercommutative, is a hypercommutative operand? So
okay, so we're really working on this right now. These are very good questions. I don't have the answer yet. That's this MGN rat is very natural in a way, I guess. So these are two very good questions. We'd be happy to dig in. I don't want to say anything about it now, especially because I'm not really an operatic expert, so I don't want to take any risks. But yeah, these are very natural questions. Yeah.
Okay.
So it seems to be the question of the handle body operand by the circle action. That's that I can say. I can't say much more right now.